Yes, sir, we can start now. I'll start the video.
Are we ready to start now?
Yes.
May I make a couple of comments before Dr. Krishna Kumar Pandey takes over? This is the second lecture in the high pressure physics course. And it's a pleasure for me to introduce my colleague, Dr. Krishna Kumar Pandey, who would be delivering this and subsequent 4 or 5 talks in continuum. And subsequently, he'll come back again to talk some other topics. Dr. Krishna Kumar Pandey joined BRC in 2004 from tennis school, BRC Tennis School Hostel, BRC Tennis School training course. And right from beginning, he has been a part of the high pressure activity. So for last 18 years, Dr. Pandey has been involved in the high pressure physics activity. All kinds, development. In that, he developed various instruments such as high pressure micro Raman, Brignon scattering, several synchrotron beamlines at school. He has been using various international facilities world over to carry out experimental work. Dr. Pandey spent 2 years in Iowa State University with the well-known Professor Valery Levitas, where he did some outstanding work on the role of the plastic deformations on phase transformations, the work which he is now pursuing also in BRC. I would leave the rest as he goes along, but I guess today's talk is essentially defining some of the basic terms in the high pressure physics. And we look forward to hear from him what he has to say on high pressure physics. Dr.
Thank you very much, Dr. Sharma. Let me share my slides. I hope it is visible to all. So here is the plan of talk. Basically, there will be total 25 lectures in this course, and I will be delivering about 7 lectures. So next 4 classes, 4 presentations will be from me. This will basically cover the basic aspects of stress strain tensor, linear nonlinear elasticity, equation of state and phase transitions. And then subsequently, in month of April, somewhere on 3 days, 8th, 12th, and 15th, I will give talks on material investigation under severe plastic deformation. So the topics that I will be covering, basically, it will be first the basics about material under stress. And in this, I will introduce what is stress strain tensor, what is pressure in solids. I will talk about linear elasticity, compliance and stiffness constants, and the effect of symmetry, crystalline symmetry on this compliance and stiffness constants matrix. And then I will talk about nonlinear elasticity, equation of state, and phase transformations. And in my second part of the talks, I will cover this solids under severe plastic deformations at high pressures. Today's talk will be up to the nonlinear elasticity. So basically, I will keep my talk to very elementary and basic level for the benefit of young researchers. So I will start with the definition of pressure in fluids, and then what happens when we go to the solid systems, what is the deformation in solids, what is the linear elasticity, then define stress and strain tensors. Then I will talk about stiffness and compliance matrix, effect of crystalline symmetry, and then how to get the information about pressure from stress tensor, and a little introduction about plastic deformation, which will be discussed in more detail in the second part of my talks. And finally, I will give a brief introduction of the nonlinear elasticity. Of course, this nonlinear elasticity is a subject in itself, very broad, so I will just cover up some introduction. Okay, let us coming first to the pressure. How the pressures in fluids are defined. So we have been learning it from very elementary levels that pressure is defined as force per unit, force upon area. So how does this definition comes into picture? Actually, this comes into picture from fluids or gases, basically. So if you go to the microscopic level understanding of the fluids, so you can consider the microscopic. There are many microscopic entities in the gas atoms or molecules, and they are basically constantly colliding at the surface of the container, and they are imparting some momentum. So basically, transferring momentum all the time. So it is momentum transfer to the walls of the container divided by the area of the container walls. So this is how the pressure is defined. And here, if you notice, I have put N here, which means that all these forces are basically normal to the surface, because in case of fluids, there are no shear stresses, as it does not have any shear strength. And that's why the basic definition of pressure comes from fluids. And this is something which is also used commonly in hydraulic presses, where we can apply small force and use fluids to basically magnify the force by increasing the area. Now, what happens in case of solids? So, if I take fluid, at all the temperatures, there will be some other pressure. I have to go to either 0 K, or I have to increase the volume to infinity in order to make pressure 0. But in the case of solids, there are some interactions between the microscopic entities, can be molecules or atoms. And because of this interaction, there is some mean position about which the system is in equilibrium. So we can understand this by a spring model, basically. So just consider a spring and a mass attached to a spring. So when it is in equilibrium condition, so there is, when you apply no force, so this system is static, it does not change the position. But whereas as soon as you apply force on this mass and you compress or elongate the spring, so there is some restoring force that tries to bring the mass back to the equilibrium position. So this is something similar to what happens in case of solids also. So for example, this is a 2D representation of solid lattice, where you can consider all these atoms connected by the springs. You can imagine a 3D network also, just similar to this 2D network, where all atoms are sitting at some fixed positions, which are connected by springs. So at any time, they are at equilibrium position. Actually, at any time, there is some temperature also. So ideally, these atoms are not sitting just at their equilibrium position. They are actually vibrating about the mean position. But these vibrations are very small. So the potential faced by each atom can be described by this kind of curve, which has a very steep rise as you go below the equilibrium distance, and it again increases if you go above the equilibrium distance. So this is the equilibrium distance, and at the equilibrium distance, you can approximate this potential as harmonic potential. So in this case also, you can define the potential energy like this, and if you take the gradient of this potential energy, which basically describes the force, again you will get the similar kind of equation that you get for the spirit. So basically your force is linearly proportional to the displacement, and the constant K here, it basically describes the elastic property of the spring, or basically the force between these two atoms. So this is basically a linear elasticity. You can understand it this way, because their force is linearly proportional to the displacement. Now, in case of solids, it is not only the normal force which acts on the surface, But because solids also have some shear strength, so even there are, if you apply tangential force, it also has a response. So now instead of expressing this displacement as a scalar quantity or a vector quantity, you need a tensor quantity to describe these displacements. So for example, if you have some body in space, and if you want to deform it, you need to basically apply some external mechanical force on this body. And as soon as you apply this external force, so there is some response force from within the material that basically tries to oppose whatever external force you applied. But before reaching the equilibrium, it also deforms. So there are some strains developed in the system and some stresses developed. So strain and stresses are basically tensor quantities, and they evolve in the system as you work on the system by some external means. So this is a representation of the stress tensor. You can see there will be 9 components in this tensor because we are in a 3-dimensional space. And by convention, this tensor is defined such way that the first indices corresponds to the direction normal to the surface, and second indices corresponds to direction of the displacement in case of strain tensor. So if you see here, this F here is basically deformation gradient that connects the description of material or sample in initial undeformed phase and in the deformed phase. And somehow this strain tensor is related to this deformation gradient as described in this matrix, this tensor here. Okay. Okay, one more thing. So as I told that this field is basically all over the sample. So here we are considering a small volume element. We call it a representative volume element. Why I call it representative volume element? Because it still describes the continuum property of the system. So it should be very small, but at the same time, it should be large enough that it can represent the continuity of the system. So you imagine there are several volume elements in this deformed system, and each element will have some values of this strain components. In case all these strain components are same in all the volume elements, then you call it a homogeneous deformation. Otherwise, it is a heterogeneous deformation. So similar to strain tensor, there is a stress tensor that also evolves in the system, which basically opposes the external applied force. And like strain tensor, stress tensor is also a field which is described all over the sample. You can consider a small volume element, and similar to strain tensor, here again the convention is same. First indices describe the orientation of the surface. By orientation, I mean normal direction to the surface, and second indices correspond to the direction of the force. So you can see if your I and J are same, means the diagonal components are there. This corresponds to the normal stresses on the surface of the volume element. And if you see the off-diagonal elements, they correspond to the shear stresses. For example, this sigma xy, it means the normal, it basically works on the plane which has a normal in x direction, and the force is acting on the y direction. So you can define all these stress components by these relations, where delta Fx is basically the force on the surface, and delta Ax is the area of the surface, and you are taking limit where the area tends to 0. But here again, I would say that the volume of this volume element should be such that it represents the system still as a continuum. Okay, now let us talk about the symmetry of this stress and strain tensor. So As I told, we are basically interested in studying the deformation in the system. So this necessitates that these off-diagonal elements, they should be equal. For example, if you take a two-dimensional cross-section of the surface and you compare the stress components sigma xy and sigma yz, so they act in this way, and they has to be equal, because if they are not equal, it means that this volume element will rotate. This corresponds to the change in angular momentum. So in order to conserve this angular momentum and no rotation in this, and purely describe the deformation of the system, this has to be equal. So what does this mean? That instead of 9 components, now there are only 6 components. So 3 diagonal components and 3 off-diagonal components. In the same way, as I described earlier, the elastic strain is also expressed like this, where u is the displacement and x is basically the coordinates in the deformed configuration. And this is how the elastic strain components are related to this deformation. Here again, in order to describe only the deformation and not the rotation, so this has to be symmetric. So from this relation itself, you can see this is defined in such way that this is symmetric. So like stress tensor, your strain tensor is also symmetric. So only 6 components for stress tensor and 6 components for strain tensor. So now come to the relationship between this stress tensor and strain tensor. So as I told, we are talking about the linear elasticity, where we are very close to the harmonic approximation. The deformations are very, very small. So you can describe that this stress tensor and strain tensors are basically linearly related. And they are related by some constants. We call them elastic constants. So if you see, this is a tensor of second rank. This is also a tensor of second rank. So this elastic constant becomes a fourth rank tensor. So total number of components in this tensor should be 81. But now let us invoke the symmetry considerations of this stress and strain tensor. So as I told, there are 6 independent stress components and strain components. So instead of writing in the matrix form, what we can do is we can describe this stress strain as a vector. So these are the 6 independent vectors of the stress tensor, and these are the 6 independent vectors of the strain tensor. And by convention, this is the direction of the components we used to write in this matrix. So first you take all the 3 diagonal components, then you go this way. So you take this component, sigma yz, then sigma xz, and sigma xy. This is how it is expressed. In the same way, you also express in the strain tensor. Okay, now this means there are 36 elastic constants. So is there any further reduction in the number of independent elastic constants? The answer is yes. Why? Because these elastic constants should be positive definite. So in order to have the positive definite eigenvalues of these tensor, this matrix, this matrix also has to be symmetric. So if you make this matrix symmetric, you will see that only one part, half the part of this matrix has independent elastic constants, other will be equal. So if you count them, it will be 21. So in very unsymmetric situation, we will have at maximum 21 elastic constants. Now what happens if you invoke the symmetry of the system? Okay, before that, let me talk about the compliance matrix also. So this matrix that I told, this is called stiffness matrix. And if you take the inverse of that, then the matrix that you get, you call it a compliance matrix. Here the unit of this constant is inverse of that of elastic constants. So here, where do you need this kind of matrix? So in some situations where you have stress components and you want to calculate strain components, in those cases, you would need this compliance matrix. Okay, now let us talk about the symmetry effect of the crystalline symmetry on this stiffness matrix. So, for example, let us take cubic system. So, as we know, in cubic system, it is symmetric in all x, y, and z directions. So, the response of the material should be same along x, along y, and z. So, all these components has to be same. Again, because it is symmetric, so all the shear components, the response in the shear direction will also be same. So, all these three, and because this is symmetric, so all these three, they can be represented by same elastic constants. Okay, one thing I missed in the stiffness matrix. So if you can divide this matrix in 4 parts. So this upper corner, this part, this basically relates only the normal stresses to the normal strains. So basically, this part corresponds to only compression. Whereas if you see only this part relates the shear stresses to shear strains. So this part relates to only shear elastic constants. Whereas this part and this part relates the shear stresses to normal strains or normal stresses to shear strain. So this part corresponds to the mixed state where there is a coupling between the compression and shear. So we encounter this situation where this will be non-zero only when system has some non-orthogonality. Okay. So in case of cubic system, because there is no coupling between shear components and normal components, all these components are zero. And in the same way, invoking the symmetry of the system, all the shear component also has to be same. So overall, you see there are only 3 independent elastic constants, which describes the cubic crystalline system. Now let us talk about other systems. So as you go on reducing the symmetry of the system, the number of elastic constants will increase. So a more symmetric case is the isotropic system. For example, glasses. It is even more symmetric than cubic. In this case, you have only 2 elastic constants. In case of cubic, as I described earlier, you have got 3 elastic constants. When you go to hexagonal phase, again based on the symmetric considerations, you have only 5 elastic constants. For tetragonal phase, you have 6 elastic constants. For trigonal phase, depending on the point group symmetry of the trigonal structure, you can have either 6 or 7 elastic constants. For orthorhombic case, you have 9 elastic constants. For monoclinic, it's 30. And for triclinic, it is 21, which is the maximum possible number of elastic constants. And this is nicely depicted here in these pictures. So here you blue circles corresponds to the equal components. And those blue dots, if they are connected by line, it means that they are all equal. And these cross mark components, they are basically related to other elastic constants. So this describes the effect of symmetry on the stiffness matrix. Okay. Now let us come to our main topic, that is the pressure. How to know about pressure from this stress tensor? When we can call there is some pressure on the system. So we can call a pressure on the system when we put a sample in some hydrostatic environment. What happens in this case? Because the shear stresses of this environment is 0, you don't have any off-diagonal component. And all the components which are normal to the sample, they are all equal. So basically, this describes the pressure. So what is pressure? Pressure is nothing but a particular stress state of stress tensor. in which all the diagonal components are in. And that is how pressure is defined as 1/3 of the trace of the stress tensor. You know that trace of a stress tensor is invariant. So this describes the pressure. Okay. And that's why in most of the experiments, high pressure experiments, where we want to study material under pressure, what we do, we put pressure sample in some hydrostatic environment, and then this chamber is enclosed in some metallic gasket, and you compress this chamber by some anvil. So if you want to do in situ studies, these anvils have to be transparent for whatever probe probe you use. For example, X-rays if you want to use, or for optical spectroscopy like Raman infrared. So these are used, diamond anvils are used, which are basically transparent to these probes. And you also put some pressure marker, which has some response, which has been well calibrated with the pressure. We assume here that whatever pressure experienced by the sample is same as the pressure experienced by this pressure caliper. So the question is whether this pressure in the sample is really scalar, or basically is it uniform throughout all the sample? So the answer is no, because many a time your sample need not be single crystal. It can be polycrystalline system. It can be polycrystalline system made up of many grains, and there may be different orientation of these grains. There may be defects in these grains. So even when you are applying pressure on this sample, means all the normal components are equal. If you try to describe the stress states within the sample, they may not be completely hydrostatic. Because here your grains are basically touching other grains. There are interfaces. So here stress state will be quite different from the stress state here, or the stress state at the boundary of the sample. So even in the hydrostatic conditions, there is a possibility of heterogeneous stresses in the sample. So, but then it means that all high pressure experiments are not truly hydrostatic. The answer is yes, but practically it is no. Why? Because under hydrostatic conditions, the difference between this normal stress component is very, very small. So to an approximation, you can consider the situation in the cell as hydrostatic. Okay, so as I told that in case of even sample in hydrostatic conditions, there can be a lot of heterogeneities. So people define macro and micro strains in the system. So what does it mean by macro strains? Macro strains means which describes the overall strain considering material continuum. So you consider there is a homogeneous strain all across the sample. So if you, this is just a cartoon to represent homogeneous or macro strains. In this case, suppose this is the undeformed crystal. And when you compress it, it deforms in the same way in all the unit cells. This is an example of macro strain. Whereas if there are some defects or some impurity in the system, locally there may be different ordering close to the atoms. So in this case, you cannot see it, but this will have different in strains. So if you define your strain tensor very locally, you will get this difference in strain components. You call it microstrains because experimentally what you are looking at the strains, it is basically the fluctuation in the strain about this macro strain. So how do you see this? How do you know about these things? You can easily know about these things from X-ray diffraction. So if you take the X-ray diffraction and suppose this is a peak that corresponds to these lattice spacings, and if there is a macro strain, what you will see a shift in the diffraction peak. Whereas if there are micro strains, you will see broadening of these peaks. So if there is a micro strain about some macro strain, you will see the broadening and the peak will be slightly shifted. So many a time in non-hydrostatic conditions, even there are macro strain heterogeneities. So within our cell, it may not be necessarily equal stress state all over the cell. There can be macro stress heterogeneities. So sometimes if your probe size, like the size of your X-ray beam is large enough that it cannot distinguish these macro strain heterogeneities, you can confuse it with micro strains. So that's why it is very important to select proper size of the beam depending on the heterogeneities within the sample that you want to probe. Okay, now let us come to the non-hydrostatic conditions. So what is a non-hydrostatic condition? So basically earlier in that case, we used some hydrostatic environment around the sample, which was the liquid, which has zero shear strength. But now we are not using any liquid. We just put the sample inside the chamber. In this case, definitely there will be some stresses which cannot be described as the hydrostatic stresses. So you can easily bifurcate this stress tensor in two terms. One is the mean stress and other is the remaining part of this stress tensor, like this. So here mean stress basically represents pressure only, because this is the mean of these three diagonal components. And if you remember, we have defined pressure like 1/3 of the trace, which is nothing but the mean of these components. So this part describes the hydrostatic part, and whatever is remaining, this describes the deviatoric part. So any general stress state can be described as combination of the hydrostatic and non-hydrostatic or deviatoric part. So it is the deviatoric part which can be different at different locations. And that's why you have lot of heterogeneities all around sample, across the sample. So in this case of non-hydrostatic condition compression experiments, you need to basically map the heterogeneities. So your probe size should be very, very small. But still it should be large enough so that you cover the representative volume in the system. Okay. Now, what happens when your deviatoric stresses are too large? Means it reaches the yield strength of the system. So, as you know, this material is basically not only composed of single crystal, it has many grains, many crystals are there. So, when you apply pressure or when you try to deform it, so first it tries to deform elastically, but beyond certain stress, what you see that stress does not increase much, whereas the strain increases. And if you leave your system from that stress state, then it does not come back to the same strain state. So there will be some residual strain. So this is very important to understand. This happens when you have multi-grains in the system. So there are many mechanisms by which the material gets plastically deformed. This deformation is called plastic deformation. There can be slip of the planes, there can be twinning, there can be grain sliding, there can be grain refinement. All these things can contribute to the plastic deformation. So how do you know whether the system has undergone plastic deformation or is still elastically deformed? You basically follow the stress strain curve. So if you release from some stress state and system follows the same stress strain curve, it means your system is deformed elastically. Whereas if you release and on release you get some residual strain, then it means the system is deformed plastically. So I would like to mention here, when we do XRD measurements, what we measure is basically elastic stress rate, because there we measure the change in the lattice constants at atomic level. And here what I have mentioned, it is the macro strain. It is not the elastic strain. It is the macro strain which includes both elastic and plastic strain. So what I mean by plastic strain, it means that whatever the macroscopic change in the dimension of the sample is there, that is inbuilt in this plastic strain. So I will talk about this thing in more detail in the second part of my talk. Okay, let us come back to the hydrostatic cases. And what we see when you compress, basically, in this plot I have shown that this is almost linear. In most of the materials at very low pressures, you see this linear elasticity kind of. Whereas in hydrostatic experiments, because the David-Torrey stresses are very, very small, and it is the David-Torrey stresses only when reach the yield strength of the material, which brings about the plastic deformation. But in case of hydrostatic environment, your David-Torrey stresses are very small. It never reaches the yield strength. So in that case, your stress strain line will continue to deform elastically. So if if the linear elasticity is a good approximation, what you should see that whatever pressure you increase, the lattice strain should be same, or the volumetric strain should be same. So it should follow a straight line. On the contrary, in experiments, what we see that when you increase the stress, the strain does not increase much. So it follows a non-linear behavior. And the reason is very clear from the intraatomic potential itself, because when you introduce large strains, your harmonic approximation is no more valid. So this harmonic approximation, whenever this harmonic approximation is valid, you are good with the linear elasticity. But when this harmonic approximation breaks, for example, in case of high pressure, where we apply pressures of several gigapascal, so the volumetric strain can be very large. In that case, you can no longer rely on the linear elasticity. Here we have to invoke the non-linear elasticity. In this case, you cannot neglect this part, which is the higher order derivative of the deformation. This is how your strain is defined in case of non-linear elasticity. And now we have to invoke higher order elastic constants in order to describe this kind of. So practically in all high pressure experiments, whatever behavior we see, it is a non-linear behavior. So I will not go in much detail of the higher order elasticity, but just to define what is the higher order elasticity. So basically, you know that the elastic constants are nothing but the derivative of the internal energy or free energy with respect to the strain. And depending on the order of this derivative, you can define this elastic constant. So if the order is second order, so still it is a linear elasticity, because the potential energy, as I told earlier, that it depends on square of the deformation. So if you take the second order, it is still a linear elasticity. But if you take the higher order derivative, then it is a non-linear elasticity. You will have several more components in the elastic constants. So this is the definition of elastic constant in case of adiabatic compression, or this is in case of isothermal compression. And if you use this term in terms of the Taylor expansion of this free energy, as you slightly deform it, because your free energy is function of your deformation, and you can get this various components. So depending on how nicely you want to describe the system, you need to invoke higher order elasticity terms. Okay, so if you want to have more details about the non-linear elastic constants, I would suggest you to go to this reference. So with this, I will end the presentation today, and in the next talk, I will talk about the various equation of state we will have described for describing the state of the system. Equation of state basically is the relationship between the thermodynamic constants. And this is important to study equation of state because one of the primary objective of doing high pressure studies is to basically study the phase transitions. One of the basic objectives of the basic physics is to study the phase transition. So in order to study the phase transition, you need to see the equation of state of the system. If the equation of state changes, that is how the phase transitions are described. So in next talk, I will talk about different equation of states people have established, which are frequently used in case of high pressure studies. And then I will talk about the phase transitions in remaining two classes. Thank you. So let me stop sharing. So now the session is open for questions. Professor Sharma, are you listening?
Yeah.
So my talk is for today. Now we can go for question sessions, or if there are no questions, then maybe
One question
we
is
can wind up.
how to determine strength.
Okay, there is one question on YouTube. How to determine stress and strain coefficients from crystal structure obtained from XRD? Okay, this is a good question. Basically, there are some other measurements in order to strain anyway you directly get from the X-ray diffraction. So if you have some ambient structure, you have some lattice constants. As soon as you apply pressure, there will be some deformations, and you easily see on the shift as the shift of the diffraction peaks. So that describes your strain components. And if you know the elastic constants of the material, you can calculate the strain components of your material. But you have to know the elastic constants. And these elastic constants can be obtained from different experiments, like Bildwer's scattering measurements or ultrasonic measurements.
Can you please explain detecting the Sambandha?
On the WebEx.
No. Whether
Okay, there is one more question in the chat box. Micro strain and macro strain. Okay, I think I shown on the slide. Is it sharing or not?
1 minute.
Let me share.
1 minute.
Yes. I think in this slide I have shown how to see micro strains and macro strain from the XRD. So if you do the X-ray diffraction measurements, and if you see the shift in the diffraction peak position, then this describes the macro strain. Whereas if you instead of the shift you see broadening, this describes the micro strain. So there are well established softwares now to analyze these diffraction profiles, and you can easily get the macro strain and micro strains. Okay. I don't see any more questions on the chat box.
Krishna Kumar, you might like to add a couple of comments as to why you went through all these details in the context of the strength issues of materials, in addition to the plastic deformation and so on. Because if the strength changes, then all these issues also become relevant as you compress the material. You might like to add one or two comments at this stage. Maybe then you can talk at more length when you give those lectures.
Yeah, sure. Yeah, actually, this yield strength of material is very important if you want to study the plastic strain-induced phase transition. That I will be covering in the next part of my talks. So basically, the main idea of the study of plastic strain-induced phase transition is to basically generate new stress concentrators, which facilitates the phase transition at lower pressures, lower macro pressures. So, but as we have seen, when the deviatoric stresses reach the yield strength, then only there will be plastic deformation. So, and this yield strength also changes with pressure. So, when we want to have all the stress strain components and not which are not completely described by the experiments, we need to combine the finite element simulations with the experimental observations in order to completely describe all the stress strains. In that case, the yield strength is used as one of the parameters. So if we know the yield strength, pressure dependent yield strength of the material, then only we will be able to completely describe the stress strain microstates in the system.
I guess no questions now.
Don't see any more questions. Then we can end this meeting now. So would you like to comment, sir?
No, I think you summarized everything very well. It will form foundations of lots of things, including when I talk about shockwave physics. Because in the shocks, unlike static pressure experiments, where there is a pressure medium, in the shock experiments, there is no pressure medium. So it is almost always uniaxial strain state. Shock is a uniaxial strain state, macroscopically speaking. Even if it is a microscopically becomes hydrostatic macroscopic strain, is still uniaxial. So some of the comments and discussion that you included today will become relevant when people investigate single crystals using shock compression.
I think with no more questions, I think we can then conclude this talk today. Thank you. So next talk will be on Friday, same time. Thank you.
Stop.
We'll stop recording.